Welcome everyone. In this video we're going to do a 14.2 problem. That's usually the limits and continuity for these multivariable functions. Here I am in 2015 fall semester. I have one of the more complicated or more difficult limit problems that we've seen on the exam, so I thought I would go over these ones with you. So in this first case, skipping ahead kind of maybe from our normal strategy a little bit, maybe you've gotten really used to seeing something like, this x squared over x squared plus y squared is something classic that kind of gets used with this squeeze theorem, right? So I'm already kind of thinking squeeze theorem on this one. Also, I mean kind of the sign also is kind of leading me towards the squeeze theorem. So let me remind you what the squeeze theorem says about things like this. And so let me go, I'm going to start with just that x squared is less than or equal to x squared plus y squared. And so basically the big thing here is that y squared is greater than or equal to 0. So basically we're just replacing the 0 here with a y squared. And sure, yes, y squared is always greater than or equal to 0. Okay, the other thing, in order to kind of get the result in this case, right, we can go ahead and add another x squared. So instead of 0 here, let me go ahead and put x squared over here. So this gives us the inequality that x squared is less than or equal to 2x squared plus y squared. So now what I can do, since this is a nice positive number, if I divide by 2x squared plus y squared on both sides, what I get is that x squared over 2x squared plus y squared is less than or equal to 1. Okay, so this is going to be the basis for my squeeze theorem here, right? So I have this nice x squared sine squared y divided by 2x squared plus y squared. And I noticed in this previous one, right, that all of this stuff right here is less than or equal to 1. So I'm going to go ahead and swap that out, and instead of all that stuff, I'm just going to put a 1 here. And here's my sine squared y. Now the other thing we have to notice is that all of this, right, we have a bunch of squaring stuff. Let's see if I can get rid of this eraser, the highlighter or not. There it goes. So yes, the x is squared, the sine is squared, right? Everything's squared down here. So this is always going to be greater than or equal to 0. This is a positive number here. Worst case, 0. So now we can go ahead and take the limit of these smaller things, right? So the limit as x and y go to 0, 0, right? For 0, well, that's constant. So that's just going to go to 0. And how about on the right-hand side here? Well, let's see. As x goes to 0, well, this is independent from x, but as y goes to 0, right, we'd get sine of 0. Well, sine of 0 is 0. Right, so we're going to have whatever this limit is, it's stuck between 0 and 0, and therefore, right, it has no choice but to go to 0. So the way that I would usually finish this up, right, this is the main idea right here, but maybe it's less formal. So I would say since the limit as x, y goes to 0, 0 of 0 is equal to 0, and the limit as x, y goes to 0, 0 of sine squared y is equal to 0, by the squeeze theorem, we know that our limit as xy goes to 0, 0 will also equal 0. And that's how I would finish this up, just so it's a little bit more formal here than just those arrows, right? We haven't maybe well defined what exactly those arrows are doing. Just by talking about it, I mean, we realize that we're taking x and y going to 0 and 0, but this is a little bit more formal, so I would include this sentence just to be safe. All right, for our second example, second limit right here, we have something similar looking, but without the sine squared and whatnot. So okay, we need to try to drive a different strategy here for maybe solving this one. So if you again think about the normal strategy, what happens if we plug in 0 and 0 everywhere? We see an x and a y, right? Well, I'd have 0 divided by 0 plus 0, so I get 0 over 0. So, okay, if I tried maybe a little bit of algebra or something like this, if I tried to factor this, you see nothing really works out. There's no cancellation that happens here. And so I'm now on to, okay, well, what if I did different paths, right? What if I did kind of a two-path test? All right, so let's go ahead and try that out. All right, so if I try something like maybe the path when x is equal to 0, so I'm going to call this path 1 here, and I'm going to say x is equal to 0 and y is trending towards 0. So if x is equal to 0 here, what I'd have 0 times y squared over 0 plus 3y to the fourth. And we're going to have 0 divided by something that's non-zero, right? This y isn't equal to 0, it's something that's non-zero that's getting closer and closer to 0. So when you take 0 and you divide it by any non-zero thing, you get 0. So this limit here, the limit when x is equal to 0 and y is tending towards 0 of xy squared divided by 8x squared plus 3y to the fourth, this is going to be equal to 0. Alright, so here's along our first path. For our second path, the claim is you can try a lot of things here, and most of them will give you out this path of 0, right? You'll get the limit of 0 for a lot of different paths. So I'm going to go ahead and try, we have to be a little bit clever here, and this is kind of, again, one of the more difficult ones that we may have seen even in class, right? We see that if we want to get these maybe powers to be somewhat the same, right? So we have y to the fourth here and we have x squared. So, I mean, if you tried something like along x equals y, again, there's going to be a power mismatch. So what I'd like to do here is, what if I try x is equal to y squared? And the claim is this will help the powers be the same, and then we'll actually get a little bit of nice cancellation here. So let me show you what happens. So if x is equal to y squared, and then we're going to have y is again tending towards 0 here. So, okay, the limit as x is equal to y squared, y is tending towards 0. And, okay, so I'm going to go ahead, everywhere I see an x, I'm going to put a y squared here. So I'm going to put a y squared times my y squared, right, replacing that first x. And then down here we have 8y to the fourth plus 3y to the fourth. And again, you can kind of see these powers now match up here. By letting x equal y squared, right, now we have y to the fourths in both of these things. All right, so this is going to be the limit as y goes to 0 of y to the fourth in the numerator and 11 y to the fourth in the denominator. And now we can see that we have y to the fourths here and here, so those perfectly cancel out, and we're going to have 1/11th. So this is going to be 1/11th is our limit. So one path takes us to 0, another path takes us to 1/11th, so therefore by the two-path test, right, the limit does not exist. So we just need a sentence to say that. So by the two-path test, the limit does not exist. And this is very important, right, that you write something like this, because this is where you've specified your answer, that the limit does not exist. If you just include the path 1 and the path 2, right, I've seen some students who write these and then say, so the limit is 0, or so the limit is 1/11th. So you really need to have that conclusion to say that you know what you're talking about. So, all right, there's this question here talking about limits in chapter 14. Again, one of the more difficult things that we've seen on the exam, so I thought this was a good one to cover. Hope you guys enjoyed. I'll see you next time.